Good morning, everyone, and welcome to this short introductory course on computer science. This course will consist of several video episodes, each around half an hour long. The main goal is to provide basic skills to those who will be attending the Polytechnic, especially for my first-year computer science course. I have designed this course to address the lack of basic skills that some students may have due to the type of school they attended or other reasons, aiming to provide a homogeneous preparation for everyone. I created this course because many students have expressed a lack of these basic skills, and I hope to partially address this issue. Additionally, I would like to give a small introduction to what computer science can do in the field of engineering and its utility, especially today. In this first video, we will start by installing a program called Snap, which we will use for the first 2 episodes. There will be 5 in total. After that, we will look at a small example of a program written in Snap. I want to make sure you understand the difference between a program created with this type of tool and a real program, like those you will create in the first-year computer science course. We will see the same example written in C and Python, and we will also look at a real application, Firefox, a browser you all know. Then, we will explore something more interesting in Snap, and I will conclude by creating an exercise for you to try on your own for next time. Now, the first thing we need to do is install Snap. What is Snap? Snap is a program developed by the University of Berkeley, which is very similar to Scratch, a well-known program designed for children aged 8 to 16. Snap is a more refined version, incorporating more advanced programming concepts, which is why I chose it. You can run Snap directly from the internet, but I prefer to run it locally. To do this, we need to download the necessary files. Here, we have launched it from the internet, but if we want to download it, we can go to the GitHub Vita repository, which is open source. Here are the instructions for installation. It's straightforward. We download the file, save it, and then unzip it. The installation is very simple. Just double-click the file, and Snap will be ready to use. So, why did I choose Snap instead of Scratch? As I mentioned earlier, Snap is more suitable for what we want to achieve. Snap allows us to create programs by assembling blocks. For example, this is the block that starts the program, and this is the block that stops it. In between, we can make the sprite move. The name, Snap, comes from the sound made when the blocks snap together. As you can see, this is a very simple program, and the purpose of this programming environment is primarily graphical. Here, we have a simple white background, but you can imagine it replaced with colorful backgrounds and different sprites. The idea behind this type of graphical language is to create animated environments or video games. Some of the most beautiful games created in Scratch have up to 80 programs, each controlling multiple sprites, with each sprite representing a character that moves and interacts with the user via the mouse or other devices. We will only see a minimal part of this because our focus is on programming, as this is an introductory computer science course. When I click on the program, you can see that it is running and the sprite moves. I can achieve the same result by clicking the green flag. If the program runs for a long time, I can stop it using the red button or pause it with the other button. If I want to duplicate a piece of code, I can right-click and select Duplicate. If I want to delete a piece of code, I can drag it here. Now, let's create a more serious program. We will start by asking the user for a number and then perform some mathematical operations on that number before printing the result. Here, we can ask the user to insert an integer. When we run this program, a bubble appears asking for an integer. If I type 12, the program ends because I haven't done anything with the number. The number 12 is stored in a variable called answer. What is a variable? A variable is one of the key concepts we will see today. As the name suggests, a variable is something that changes over time. It is a container that holds a value, which can be of different types. In this case, an integer like 123. This number can change over time because we need a new number, so we store it in this container. After asking the user for input, I have the variable answer containing 12. To display it, I can use a block that says, say, for 2 seconds. Instead of saying, hello, I can say, answer. So, I ask for a number and then display it in a bubble for 2 seconds. If I run this, I type 12, and it displays 12 for 1 second. We have created our first program, but I want to make it a bit more complicated by performing a simple mathematical operation on the number. I know the number is stored in answer, but I want another variable to act as a storage and then increment that value. So, I create a variable called number. The main concept of a variable is that it can take on different values, but at any given moment, it will only contain one value. For example, in quantum computers, a variable can hold multiple values simultaneously, which is quite counterintuitive. Now, I want to load the value from answer, which is 12, into number. I use the set block to assign the value of answer to number. After this block, I want to increment number by 5. I use the change block and set it to 5. This block adds 5 to number. If I set it to -5, it would subtract 5 from number. This type of block represents what in programming is called an assignment. In this case, it's more of an increment or calculation. Now, I want to print number. Instead of printing answer, I drag this block and insert number. All blocks have a specific shape, like puzzle pieces, and are designed to fit together. The stop block at the end has no further connections. Now, we have a program that asks for an integer, loads it into number, increments it by 5, and prints the result. Let's try it. I type 12, and it prints 17. Now, I want to make it a bit more sophisticated. Instead of just printing number, I want to print a sentence like, the number now is. To do this, I need to use operators, specifically the join operator, which combines two pieces of text or numbers. Here, I can write the number now is, and then insert number. This green block is the combination of the number now is and number. Now, instead of saying hello, I say this combined block. When I run it, it asks for an integer. I type 12, and it prints the number now is 17. We have seen our first program, which, although simple, is quite refined because it contains the concept of a program as a sequence of instructions, in this case, blocks, the concept of assignment, arithmetic operations, input, data entry from the keyboard, and output, displaying the result. It also has a clear start and end. Now, I want to show you the equivalent of this program in the two main programming languages used in the first year. First, here's the same program written in C. If you compare them, you can see that apart from some details, this is the declaration of the variable number, which we did through the menu in Snap. Here, the scam function reads the number and assigns it to number. Then, number equals number plus 5 inches corresponds to the change number by 5 inches block and snap. Finally, the printf function prints the result. This is the basic mechanism of input, processing, and output, which is common to almost all programs. Now, let's look at the same program in Python. The Python program is even simpler. We use the input function to ask for an integer, convert the string to an integer using int, and store it in the variable number. Then, we perform number equals number plus 5 and print the result using print. Again, we have input, processing, and output with a nearly one-to-one correspondence with the snap blocks. Now, to give you a clearer idea of what a program is, you might say, but these are toy programs. Well, here we are using the Firefox browser. Firefox is a significant program, and if you look at the number of lines of code, assuming 1 line per statement, it's around 6 lines, similar to the C and Python examples. However, the equivalent program that controls Firefox is much larger, with over 1 million lines of code. During the first year computer science course, the programs you will be asked to write will be around 100 lines of code, which is much more manageable. Now, I want to show you the code of a program like Firefox. Firefox is open source, so the code can be downloaded. I have downloaded it to show you. Here is the folder containing the source code, which is quite large. You can recompile the entire program from scratch if you want. For example, here are many directories because 1 million lines of code can't be in a single file. Let's open one of these files. We need to open it with a text editor like WordPad. This is a small part of the program written in JavaScript, a close relative of JavaScript. Firefox is partly written in JavaScript, but also in other languages. For example, here's a Python file, and here's some C++ code. Overall, Firefox has over 1 million lines of code. To give you an idea of the enormity of this number, the Treccani Encyclopedia, composed of about 50 volumes, each with 2,000 pages and 50 lines per page, totals around 5 million lines. Firefox has at least 1 million lines, which is 1/5 of the Treccani. Writing the Treccani is no small feat, and writing Firefox is equally challenging. Similarly, the Windows operating system, which is itself a program, has around 20 million lines of code. A couple of notes: these programs are not perfect. Software engineering, a branch of computer engineering that deals with software design, has some empirical rules. One rule states that for every 1,000 lines of code, there is 1 error or bug that cannot be corrected. This means Firefox, with its 1 million lines of code, could have around 1,000 uncorrected bugs that may cause occasional malfunctions. Another interesting number: how long does it take to write such a large program? Another semi-empirical rule of software engineering states that a professional developer writes, on average, 10 lines of code per day. This number seems small, but it includes the entire design and testing phase, which is very complex. Writing a small program like the one we did is one thing, but writing a professional program that must work perfectly is another. After this brief excursion, aimed at giving you an idea of what we are getting into, even though we will deal with much smaller programs, let's look at some other small examples. We have seen our first program. Let's delete it and look at something more interesting. Earlier, I showed you an example where I made the sprite move. This programming environment is designed for video games and animation systems. Let's make the sprite move and rotate. When I click the green flag, the sprite moves and rotates simultaneously. This means we have 2 programs, or scripts, acting on the same sprite at the same time. This is a multi-threaded program, where multiple threads or programs work together. In this case, both programs control the same sprite, making it move and rotate. This is quite sophisticated, as creating a multi-threaded program in C is much more difficult, and even in Python, it's not trivial. Now, I can do more. I can add another sprite. Here's a new sprite, still an arrow, but I can replace it with anything. The background can also be colored. Now, my program has disappeared because these were the scripts for the first sprite. This is the second sprite, which can have its own scripts. If I copy this script to the second sprite, I can run both scripts together. The dark gray sprite rotates around a hypothetical center, while the blue one moves. Again, we are using a multitasking program composed of two processes. These two processes do not explicitly communicate, while these two threads do because they both control the same sprite. This seemingly simple task is quite complex and involves non-trivial complications that we will briefly discuss in one of the next episodes. Now, let's do a few more things before finishing this episode. First, let's delete the second sprite and try something more refined. Let's start by resetting the sprite to its initial position. Here, we can imagine a Cartesian plane with the x and y axes. The origin, 0, 0, is here. We can also set the direction with 90 degrees pointing to the right. Now, I want to make the sprite draw a small square. It should move 20 steps, turn 90 degrees counterclockwise, and repeat this 4 times to return to its starting position. Let's try this. The sprite moves very quickly, so I can add a wait block to slow it down. Now, I can duplicate these blocks and repeat the process 4 times. This way, the sprite draws a square. To make the square visible, I can use the pen blocks. At the beginning, I clear the canvas, move to the center, lower the pen, and start drawing. After drawing, I lift the pen. Now, when I run the program, it draws a square. Now, I want to do something more. Instead of moving 20 steps, I can create a variable to control the length of the side. Let's create a variable called side length. I can ask the user for the side length and store it in this variable. Then, I can use this variable to control the movement. For example, if I set the side length to 50, the square will have sides of 50 units. Finally, if you want to save your program, you can export it as a project. For example, you can name it Square and save it as an XML file. You can then import it later to continue working on it. The exercise for next time will be to modify the program to draw a polygon with a variable number of sides. Instead of a square, you should be able to draw a polygon with any number of sides. This will involve creating a new variable for the number of sides and adjusting the angle accordingly. We will work on this next time. That's all for today. Thank you.